In this video, we're going to look at how you go about differentiating natural logs. And so this is the formula for the derivative of a natural log that appears on the formula sheet. A little bit misleading because it doesn't in any way apply the fact that log functions have an implied domain. So log to the base e of anything has a domain where whatever that thing is in there has to be greater than 0. And so what you have here is a function that only exists for positive real numbers, and the derivative of it is a formula that exists for, if it is just the formula, the hyperbola, has a domain that's actually all real numbers except for 0. So you have to be careful. The derivative of the log function's only going to have a restricted domain of the original function. Plus, if there's any undifferentiable points that pop up in the domain as a result of this particular value, that will be the case in the derivative as well. So by all means use the formula, but remember it has a restricted domain, and I'll show you more about that in a sec. So again, I'm going to move this point along this log curve here, and we're going to track the position of the point. So these are the coordinates of the point, this point here. And we're also going to look at the gradient of the tangent as we go. So you can see that the log function does not exist for x values that are 0 or below, and so our derivative graph isn't going to have any values over here. And so as we start off right down the bottom here, as close into 0 as we can, we are going to have a positive gradient, and the gradient is going to be super duper large. So up here, up the top here, we're going to start with a very, very large gradient. And let's watch what happens as the point gets pulled along the curve. So let's have a look at the size of the gradient. So you can see that as the x value increases, you can see up here that the gradient is decreasing, decreasing, decreasing. And so our graph, as we generate our gradient graph, is doing this. At x is equal to 1, the gradient is equal to 1. So at x is equal to 1, the gradient is equal to 1. And as you can see, even as we continue out to the left-hand side, the gradient is still positive. Still positive. It's small. Come on, point, move. There we go. It's small, but it's still positive. And so what we're generating is the right-hand branch of the derivative, where x is greater than 0, and it's the greater than 0 section of the hyperbola that you get as your derivative. So definitely the derivative of a log function is part of a hyperbola, but I find that actually using the chain rule with derivatives for natural log gives you a much more useful formula. So if we put a function inside a log function and we find the derivative of that, so f of x is our inner function and our log function is our outer function, if we use our chain rule, then the derivative with respect to x is the derivative of the inner function, which is f dashed of x, times by the derivative of the log, which is 1 over f of x. If we put that together, we get that the derivative of a log is the derivative of some function over the original function itself. So this is a much, much more useful version than what's on the formula sheet. And again, be super duper careful with your domain for your derivatives. And so I'll explain what I mean. So this particular function here, f of x, is log to the base e of x squared minus 4. So we need x squared minus 4 to be greater than 0 for this function to exist. And so what I've got here, this black line is the graph of x squared minus 4. And our log function only exists for values where that parabola is greater than 0. So we're talking about these sections here. So our log function actually only exists for these values here, this way and this way. That's our domain. And you can see that I've actually graphed our log function here in red, and you can see that it asymptotes along that line. Now that line there is in fact the line x is equal to 2. And our function doesn't exist in the blue section between those two asymptotes. So you can see our actual log function itself has a right arm and a left arm. And what I've done is I've also asked my CAS calculator, you can see that I've instructed it to draw the derivative of that log graph. And it's got some beautiful derivatives here. There's our exponential over here. And because we've got two log graphs sections in our original function because of this squaring thing, we've got both arms of the hyperbola. But the CAS calculator has also thrown in for us this pink line, which is now purple because I've coloured it in, this pink line in the middle, which it shouldn't have because there's no function there. So what in fact is the CAS calculator doing? Well, what the CAS calculator is in fact doing is it's graphing. If we found the actual derivative for this formula up here at the top, so f dashed of x is the derivative of that inner function, which is 2x, over the actual function itself, x squared minus 4. And we graphed that function. That function actually exists in the section of the domain that we are supposed to be excluding. So if we actually got the CAS calculator to graph it, which I've done here, you can see that that is exactly the graph that we get. So you need to make really sure that when you're going to graph the derivative of a function, particularly a log function, that you're thinking about the domain that that log function is defined for, and only taking whichever section of the hyperbola that you get as a result, whatever section of this particular formula you get as a result, that it is in fact defined within the domain for this log function. Other than that, finding the derivative of log functions is actually quite simple. And so we're going to find the derivative for log to the base e of x squared. And so our derivative for this function is in fact the derivative of the inner function of the log, so 2x divided by the actual function itself. And we can tidy this up by dividing the top and the bottom by x, and that will give us 2 over x. This second function is in fact a composite function, and so what we need to do is to find the derivative of the inner and the derivative of the outer. So let's do that. So from the inner function, we get the derivative of 1 over x, and from the outer function, which is just a squared function, we get 2 times log to the base e of x. When we multiply those together, we get 2 over x log to the base e of x. No problems at all. If we had to sketch that derivative, we would be needing to make sure we're looking out for implied domains for the log and implied domains for our fraction here.